All right, so in today's lecture, we're going to go over stresses and how those different types of loads cause different types of stresses to develop in uh, in a structure or an element. Okay, and so if we want to find the state of stress in a machine, we have to determine the loads. We usually use that using our statics and dynamics. And then we have to find the internal forces using what we know from mechanics of materials. The four types of stresses that we see in machine elements are due to axial stress, bending stress, shear stress, and torsional stress. And we're going to talk about how the bending stresses and shear stresses are developed in a material, and then talk about the torsional stress and combine them. So recall that a state of stress is at a point in a material. It's not across an area or cross section, but it is actually at a point. And so when we talk about stresses, we're really trying to find the points of the material in a design that is going to experience the greatest state of stress. Okay, and the state of stress can be fully triaxial, and here this is called a stress tensor. And in this tensor, we can capture all of the stresses on a very, very, very small point of material represented by this cube. And we're only showing 3 of the faces, but the other 3 are hidden just to make it easy. But we have our stresses on the faces. Those are our normal stresses, and then we have the stresses that are along the face, and those are our shear stresses. So the first element detects the face and then the direction. Okay. This general state of stress can be represented in a stress tensor, and then we can have that state of stress along a direction. And if we can find these directions here, this is the unit vector normal to the principal plane. This should be principal, not principal, but this is to the principal plane. So there's some orientation where you have your maximum stresses, and if we can find this sigma, then we can find our principal stresses. So this equation here for this three-dimensional state of stress is actually what's called an eigenvalue problem, okay, in the form of ax is equal to lambda x, which is the same as lambda times the identity matrix, where lambda is a scalar. So we can rearrange these equations like this. Ax minus lambda I, this is from linear algebra, and find that vector that maps, find this matrix here that's mapped to the null space. So that's your eigenvalue problem. So for this to be true, we can't have a non-trivial solution, and therefore ax minus lambda I inverse must not exist. So that or ax minus lambda I must be a singular matrix, which means that it's not invertible, and that means the determinant is 0. So that's what we can use to find the values for sigma in this eigenvalue problem. Don't worry if you don't completely follow. This is just sort of to give you the picture of the underlying math that allows us to get the principal stresses from a state of stress tensor. Okay, so if we solve this problem, saying that the determinant has to be equal 0, we get an expression like this, where we have a cubic term in terms of principal stress, and then we have these coefficients, which are called the tensor invariants, times sigma squared, sigma, and sigma, and then a constant. And what this is this is actually a stress function that will map out through our principal stresses. It's a cubic function that'll map out our principal stresses. These tensor invariant coefficients can be found just from the state of stress. And then the principal stresses we can solve for the roots of that cubic equation. There is an analytical solution for that, and we can find sigma 1, sigma 2, and sigma 3. And what's important to note is that we have this three-dimensional state of stress represented by this stress tensor here, and going through this process here we can find the principal stresses. We have easier ways to do that for plane stress. We can use Moore's circle, and we'll talk about that in the next lecture. The typical notation is that sigma 1 is always greater than sigma 2, which is always greater than sigma 3. Okay, and in plane stress, often one of these, in plane stress, one of these principal stresses is 0. So we can treat it like that. We can also use the transformation equation given a state of stress in Moore's circle for two-dimensional stress instead of solving the eigenvalue problem. And we can find the principal stresses once we get the normal stresses to find the principal shear stresses using these equations here. And these are the 2D in plane principal stresses. This is Moore's circle. This is your center. This is your radius. And we'll talk about that. And this is your max in plane shear, okay, which is equal to the radius here. All right. And we'll derive those in the next lecture. But for this lecture, what we really want to cover is the forces that are present in machines. And so we have our axial loads, which is just our axial load over the area. We know that. The stresses right at the load are not equally distributed, but because St. Venant's principle, some distance below that material, the stresses are uniform enough for us to consider this simplified version for axial loading. We have shear force in materials. That shear force V leads to a shear stress distribution across a cross section here. This is your shear V, this is your area A for some cross section of a material that has transverse loads. And we have the shear formula, which we'll derive for you today. This is V is the shear, I is your moment of inertia, T is your thickness of the cross section, and Q is this value here, which is y bar, which is the distance from the neutral axis to the centroid of A prime, and A prime is the area of the member's top or bottom cross-sectional area above or below the plane where the thickness is measured, okay, and where we're trying to calculate the shear. So we would have the shear force, the moment of inertia, the thickness, and then we'd have this area above the plane of that thickness, that area above. We'd have the centroidal distance to that area, and then that area itself above. If we just use the shear stress V over A, that's our average shear stress. But in reality, there's a difference depending on how big the cross section is. It turns out that the calculated shear is actually going to be smaller than the actual shear that you see at the ends. Okay, so just keep in mind that these are average shear forces and that the shear is actually a little higher depending on the cross-sectional shape. We can't just plug these numbers in without remembering some of these caveats. Okay, and then we have bending in members, and that bending causes a bending moment on the cross section of a material, and that bending moment causes what we call bending stress. and we can find that bending stress either in straight beams or curved beams using these formulas here. This is our flexural formula. This is my over I, where I is the distance from the neutral axis to the top of the beam, m is the applied moment, I is the moment of inertia. And then in a curved beam, we have my. Instead of over I, we have to change the geometry to the curvature. And we have A, which is a cross-sectional area, E, which is the eccentricity, and then R minus Y. And then E is defined as R, which is the distance to the neutral axis, minus R, which is the distance from from R to the centroid. And we'll show you those equations as well. And then the fourth loading condition that we get is when we have an applied torque. Then we get a torsional stress, which is a shear stress in a material. And that is proportional to the applied load and the distance from the center of the shaft divided by the polar moment of inertia, which is the distribution of the area from the center of that shaft. And it's a measure of its resistance to torsion. Okay. If we have closed thin wall tubes, we get this simplified expression here, and these equations do show up on your FE exam, and if you're interested in going through to get your PE, the FE is the first step, and these are all things you have to remember. Okay, so the shear stress we could find for a thin walled tube, or a uniform cross-sectional tube using these equations. So the first thing we're going to do is talk about the flexural formula, which is the bending stresses that are developed in beams. Of course, we have beams that have different types of loads: simply supported, cantilevered, overhung. And when these are loaded, they develop their internal shear forces, and we know that the bending moment is the integral of the shear at that point. So we often need to know where the maximum shear forces and bending moments in a beam, so we can calculate the bending stresses. Okay, so we've spent some time on calculating the load, shear, and moment diagrams as a function of the distance in the last homeworks. So in this case, we want to find where that max moment is, and then we can find out what the bending stress is using the flexural formula. Okay, so when we bend beams, keep in mind that the material on the top, if we bend it with positive moment here, which tends to make the beam smile, then we have compression on the top surface, we have tension on the bottom surface, and in between we have the neutral axis, which doesn't change shape during bending much. The top surface is in compression. It has this stress distribution, and then tension on the bottom for this loading case. This is the flexural formula that describes the bending stresses that occur due to an applied moment. Okay, if these are the stresses as a function of the distance from the centroidal axis. If you're all the way at the end where you're at the surface, then you just use C. That's where your max bending stress is going to be. And keep in mind that's on the element of material, okay, that is at the surface. I is our centroidal moment of inertia. You may see this S, okay, in many structural handbooks. Civil engineers use this regularly for beams, and it is called the section modulus, and they use that to calculate the bending stresses. Okay, so then instead of having your C and I terms and calculating them, they'll give you a beam with a certain shape, and you can go look up the section modulus for that beam, and then all you have to do is divide the moment by the section modulus to get your bending stresses. So they give you these properties for specific beams, and if you know the applied moment, then you can quickly get the stresses. Keep in mind that when we're bending an element, we have compression at the top, we have tension at the bottom, And this is an exaggerated view of what a beam might look like if it is in subject to a bending moment. It kind of smashes at the top and stretches out in a weird shape. And so as long as we have loads that are well below, and we don't have super thin cross sections, then we can use these use the flexural formula in analyzing these beams. Okay, the strain distribution. The strain is going to be linearly proportional to the distance from the neutral axis. So we have the maximum strains at the top and bottom surfaces, and that's how those strains are distributed. The max strain is going to be at the top surface for this case, okay, for this load, for this moment condition, moment load, okay, and the max stress is linearly increasing as you go away from the neutral axis, and the max stress is at the end. Okay, so if we represent the state of stress as minus y over c, where that's the linear distance ratio to the top surface, then we can just multiply that by the max stress. Okay. If we need to find the neutral axis for a beam that's not uniformly shaped, the definition of the neutral axis here is where the resultant force on a cross section is 0. Okay, so if we have a bending moment, we have these two different states of stress. We have this tensile stress distribution on the bottom. For this positive moment, we have a compressive stress distribution on the top. Okay, so the neutral axis is where the resultant force on that cross section is 0. So if you integrate those forces over the area, it's when it's the place where that integration is 0. So we can do that for this example, and then show that this happens when the integral of y times dA, which is the first moment. Okay, so that means that the first moment of the member's cross-sectional area has to be 0. Okay, that only happens if the neutral axis is the centroidal axis for the cross-section. So we can find the centroidal axis for the cross-section, assuming we have uniform material properties for that cross-section. Okay, so if you find you don't have a shape that you can look up, you can still find that centroidal cross-section, use it as your neutral axis. Okay, so we get our flexural formula here by saying that the moment that develops is equal to the integral of y, which is the distance from the neutral axis, times df. And you can see that right here, that term is, you have y is your distance term and df is your differential force. So you're multiplying a moment arm at some distance y with some force df, and your moment is just the integral of all those little df forces. Okay, so instead of representing df as df, we can represent it as sigma dA. And then we found that sigma, if we say that it's linearly related to the distance in terms of y over c times sigma max, then we get this expression here, which is y squared dA over c. And if sigma max is a constant, we can pull it out. And then we can express our moment in terms of sigma max over c times y squared dA, and y squared dA is just the definition of I, the moment of inertia for that cross section. And that's where we get our flexural formula here, which is mc over I, by rearranging those terms. Okay, so this is just a review. This is just highlighting that we can calculate the moments using the flexural formula, which is simple. Here we have an applied moment, and we also are given the stress distribution. So if we calculate using the flexural formula with a given moment, okay, we can calculate that the moment is 24 kip foot, which is a weird unit. It's 1,000 inch-pounds foot, 1,000 pounds force times feet. And then here, if we looked at the resultant of the stress distribution here, then we can take the centroid, or take the force and put it as in the center of the distribution here, like represent that force distribution as a point force, multiply it by the distance, and we get the same value for the force as we do for the flexural formula. Okay? All right, so that's where that comes from. Now, we often have curved beams. Okay, for example, this is an arbor press. It has a curved beam. So we also have to design for curved beams. These are the terms that we need to understand, and we have this variable E, which is the distance from RC. RC is the distance from the center of the curvature here for that curve, for the curved beam. It's where that center of the circle would be on that curve. And then A is the cross-sectional area, and we divide that by the integral of dA over R, and then we get this term E. Then we can include this term here that'll count for the curve in the beam. This sigma I is the inner stress, okay, and then sigma O is the outer stress. This E accounts for the shift in the location of the neutral axis, okay, at this cross section, and we have to account for that in the curved beam because the stress distribution is different and the neutral axis is dropped down in this case for this shape of beam. C naught is the distance from this shifted neutral axis to the top surface, and Ci is the distance from the shifted neutral axis to the inner surface. Okay, so these are the variables that we'd use, and if we can calculate those, we know the applied moment. We can calculate E for different cross-sectional areas, and then find the inner and outer bending stresses. If we also have the presence of a load, like the arbor press here, we can take the free body diagram. In this case, on that inner face and outer, the inner and outer profiles, we can include that force as just the that shear force that is there across that cross section, and it contributes to the state of stress on the inner and outer faces for curved beams. Okay, so now we're going to talk about shear in a straight beam and transverse shear as well. So this is we just talked about the flexural formula and bending stresses. Now we're going to talk about how shear stresses are developed. Okay, so shear, we have when we take a cross section of transversely loaded member, and that shear acts across the face. And so if we were to take out one of these points inside of a cross section, we could take a look at it, and we have this force, the stress here across this area. So that stress times the area is going to be a force, a downward force. It has to be counterbalanced by an upward force. And those two forces on the front face and the back face create a couple or a moment, okay, that has to be counteracted by these longitudinal shear stresses at the top and bottom faces. Another way to think of it is you try to pull this material down and out of the beam. It's going to have this resistance to pulling at the top surface. So however you want to think about it, you can think of it in terms of the balance of forces here, and if you take those forces across the center of this cube, it would cause it to rotate and spin, okay, because it's a couple. It can't do that, so it has to have a resisting moment. The resisting couple or moment is provided by the material above and the material below. So that's how we get those shapes. This should all be a review to you, okay. Shear and beams, when we have shear, in fact, you'd actually get sliding if you allowed the various cross sections of the material to move. If you constrain their motion and you prevent them from sliding by gluing them together, then you actually get some warping of the cross section. Okay, So at some point, the theory is valid. It's sufficient for us to calculate loads. But if you get very low stiffness material and you get sufficient warping, it's possible that you'd have to consider a little bit more detailed approach to calculating the shear stresses. Okay. The warping violates that assumption of a plane section remains plane, as we saw in axial loading, torsion, and bending. Okay, but if we assume it's small, which is the case for slender beams, okay, we can still develop this relationship. That relationship between shear force and shear stress is called the shear formula, and that's it here. We talked about what each one of those terms meant at the beginning. Okay, this is a derivation of the shear formula. Okay, so we can derive the shear formula of a cross-section by considering generalized loading condition, and that where we have, as you can see here, we have distributed loads, we have point loads, we have point moments, and we have reaction forces, and we can consider some small element here, and then say, what are the shear stresses that are there. You may say, well, why are we going through this? This is material that's covered in the mechanics of materials class. Well, we're covering it because in machine design, I still think it's really important for you to kind of see where things come from. Okay, so this is just a slide for you to be able to go back to the basic theory, and all we're really doing is summing forces, okay, and moments to zero. So if we look at a cross section here, this is our neutral axis. We have these loads on each side. We have these moments, and if we have the left side, we have some applied moment. On the right side, we have some applied moment for plus this differential increase or decrease in moment. Over here, we have df prime, double prime. Over here, we have df prime. So these are equal and opposite with maybe some small difference, and that's accounted for in this dm moment term. The point is, you can have if you have different forces on different sides, then you can still look at the equilibrium, and it just allows you to introduce more terms. Okay, so if we take a cross section here, this is an element that has subject to some shear. It has area A prime. We're looking at this element here at this slice. Okay. It has thickness dx, and it has stress on the back surface of sigma, sigma prime on the front surface, moment on the back surface of m, moment on the front surface of m plus dm. Okay, and then what we can do is take that slice and then look at that shear force and find out if we can express this shear force in terms of these stresses and moments. Okay, so that's what we do here. We say the sum of the forces on a cross section is 0. And that means that sigma prime dA prime minus sigma dA prime, so those are our two different stresses, sigma, sigma prime, minus your shear stress times your thickness times dx. That's the area that the shear acts on here. This shear times this area here. We say, well, if we sum forces, these are the forces, they sum to 0. Okay, and then if we sum moments and say they're 0, then we can also introduce the shear stress, and then we can rearrange these. Oh, actually, sorry, we just expressed the stress here using the flexural formula. So these are the bending stresses. Okay, and then if we do that, we can collect terms, and then we can isolate the shear stress on the one side of the equation. If we do that, we get this expression, 1 over it dm dx integral y dA. dm dx is the derivative of the moment diagram with respect to x. We know that that's the shear. Okay, not the shear stress, but the shear force. The centroid of A prime is y prime bar, and that's actually this expression here. Okay, so we can replace this expression with y bar prime times A prime, and we call that Q. Okay, so that's where that variable Q comes, and that's the shear formula. Okay, so we get the shear formula just by balancing the stress, the forces in a cross section. Okay, and that's the shear that develops on some section here with a shear V, and that V came from the dMdV, which is pretty interesting. And this Q is y prime a prime. The Q is y prime is the distance to the centroid of this area, and a prime is this area above this slice, and that's T, that thickness T. Okay, these details are important for you to understand where we're actually calculating the shear stress. So we can actually calculate the shear stresses using the shear formula at different locations along the thickness, but we just have to make sure our area, centroidal area, and shear and thicknesses and moment of inertia are used properly. Okay, this is what I was saying earlier. When we have a rectangular cross section, so this is a thinner rectangle, then and we calculate the shear using the shear formula here. That's this this dotted line, but in reality the shear force that's developed is actually a little bit higher. Okay, so for thinner beams, slender beams, they're close, okay, within 3%. For thicker beams, this shear stress distribution looks more like this, okay, where this is your flexural formula here. That it's confusing the way these arrows are, but this is your flexural formula, and it is the average stress on this cross section. Now, but in reality, if we calculate the actual stress at that location, it's actually 40% higher. Okay, and that's a big deal when you're designing machines. So if you have a wider cross sections, you need to make sure that you're within the stress limits for that design. We often have wide flange beams where we put the mass far away from this axis. Okay, the farther that we put mass away from an axis that runs perpendicular, the greater the moment of inertia is, and the moment of inertia is the measure of the resistance to bending. So if we want to resist bending, we should move the area as far away from that axis as possible. So that's why I-beams are shaped the way that they are. Okay, and so we can use the shear formula for wide flange beams, but we shouldn't use the shear formula for cross sections that are really short or flat and not really at points of a sudden cross-sectional change, such as a flange to web junction in a wide flange beam, and not at a joint on an included boundary. Okay, and so it would take a little bit more than we cover in this class, but you need to be aware of that. Okay, so this is a wide flange beam. The shear is 80 kilonewtons. This is just an example of how we actually use those equations. Okay, so we can look at the shear formula at different points. Remember, the shear formula is the thickness and then the A prime above it. So it's interesting, if we calculate it at this point B prime, the shear stress at B prime is 1.13 megapascals. If we drop down here to this part, the shear stress actually jumps up because the shear is distributed across a much smaller area. Okay, and so you can see how that distribution of shear stress jumps. I'm bringing this example in here just so you can take a look, see how those stresses look as a function of the cross section. Okay, which is interesting, and we still have our max shear here at the center. Okay, so these are just how those other values are calculated, in case you forgot how to calculate your shear stresses. The other thing that we have to consider is the shear flow in a lot of designs, and we'll talk about this something similar when we get into welding. But the shear flow is the shear force per unit length along the longitudinal axis of a beam. Okay, and that's important when we look at joints that are bolted or screwed or riveted or welded or nailed, because those fasteners are going to have to pick up that shear flow for that element. Okay, so if we have say a moment that's applied to two sides of this T cross T sectional beam, then we can do is calculate that shear, okay, that shear flow, which is the shear force per unit length. So the longer it is, the more shear force is going to have to be consumed. So we can calculate the number of fasteners that are needed, or the number of weld or spot welds, or how long a weld needs to be in order to pick up that that shear force in that member. Okay, so as you can see, we have different options when we're joining things together. We can come like this or sideways. That shear flow that we care about is going to be this shear flow, this dark black line here. Okay, and we're considering it with respect to the neutral axis of that assembly. So that y bar prime is the distance to the center of that body where those fasteners are put in. This is an example, and it says, hey, what's a better way to make this beam? Should I put the nails like this, or should I put the nails in the side? Okay, and so the question is, what is the, how many nails do we need for a total shear strength of 40 newtons? Okay, we could make it either in case 1 or case 2, and the question is which one requires more nails. So maybe you can ask yourself, you can think about it for a second. Well, if you don't know, we can calculate it. So we can take case 1. In case 1, we got to calculate Q, which is y bar prime times A prime. Okay. And we're told that the distance across here is 30. Okay, so this A prime here is 30 times the thickness 5, and then y prime is the distance from the center to the center of this member. Okay, so we can calculate that, and we find that the shear flow for this member is VQ over I. Okay, so we use VQ over I, and we find that the shear that's developed, okay, is 27.1 newtons. If we go to the second case, there's a single row of nails that holds one side of the boards to the web. Okay, and in this case, the shear that they are going to experience is 81.3 newtons. Okay. And the reason is that this A prime area is a lot smaller. Okay, so when we find the shear, we would divide it by the Q. Okay, in this case we have 10 here times 5, so we have that smaller area that it develops over. Sorry, I noticed a typo here. This was pounds, so I fixed that. Now, this says that the nails have a shear strength of 40 newtons. Okay, and they're spaced at 90 millimeters, so the shear flow is going to be 40 over 90. Gives us a unit of force per distance. So then determine the largest vertical shear that can be supported in each case. Okay, so the first case, I is the same for both cases, but for the first case, we have we can use our shear flow, which is 40 over 90, to calculate the shear that we can hold with those loads. Okay. So the largest vertical shear that we can hold is 27 newtons in this case. In this case, we have twice as many fasteners, but we actually get almost over twice the shear that we can hold by having these fasteners in this location. Okay, so that's using the concept of shear flow to find out what shear we can sustain if we space the fasteners at a distance. Okay, and we could use something similar for welds or bolts or etc. By knowing the shear strength per distance that we have them assigned. Okay, so the last loading review that we're going to do is for torsion. If we have a moment along the longitudinal axis, it's called a torque. Okay, and this type of load is a torsional load. And we have this distribution of stress from this load, and it's the maximum at the outer radius r. When we use torsion, we have to make some assumptions. And that is that the element that we're analyzing is distant from the applied loads. It's similar to the St. Venant's principle. So if we're going to analyze the stresses, we're not analyzing right at the applied load, we're analyzing them somewhere like over here. It's subjected to pure torsion in a plane that's normal to its axis, and no axial bending or direct shear loads are present. Okay, we're treating it by itself. We assume that the cross section of the bar remains plane, that the bar is homogeneous, isotropic, and obeys Hooke's law, and the stresses are below the elastic limit, and the bar is initially straight. So those are some of the assumptions when we use this formula. The formula here is just the applied torque times the distance from the center point over J. Okay, and J is that polar moment of inertia for a cylinder. Okay, we have this expression for a tube. We have this expression for J. And the deflection angle here is the applied torsion times the length over J times G, where G is the shear modulus, which is related to the Young's modulus and the Poisson's ratio. Okay, and this shows up for everywhere, and the circular cross section is actually one of the best shapes for torsional loading. That's why you see it in all over machines. When we have non-circular cross sections, we can use the cross-sectional factor Q and K, factors Q and K, to find the shear stresses and deflection. Okay, if we have K and Q, we can just use them directly to find the stresses from an applied torque by using these formulas here that we can plug in. These are from your book. So if we want to find the deflection, we use K. Okay, G is the material property, T is the applied torque, L is the length. So we have different factors here for Q. And then if we want to find for K for the deflection, and Q for the finding the max shear stress in a cross section, that's 4 different shapes. This is an example here. We're not going to go through it, but I'm pointing your attention to it in the book. You should go through it, see how they calculate K for the deflection and Q for the applied shear stress. And what the question that they're asking is determine the best cross-sectional shape for a hollow torsion bar to be made from a sheet of known dimensions in order to withstand the pure torsional load with minimum angular deflection. It says also find the maximum shear stress, and it gives you these different geometries to take a look at. What's interesting is the result. Okay, if you have this situation here, then the angle of deflection is 214 degrees. If you have this shape here and it's open, your deflection is actually 219.6 degrees. So it's almost the same as if you had a wire. Okay, if you have a square cross section, the deflection is 0.51 degrees, and if you have a tubular cross section, the deflection is 0.31 degrees, and the shear stress is 1,000 psi versus 42 or 45,000 for these open shapes. So another way of thinking of that as well is if you have a tear or a slot or whatever, and you have a torsional load, that the loads go from normal, but if it's cut and that cross section is compromised, those shear stresses jump up to 45, 42 times the stress that you have in that state. So how do we put all this together? Well, we have axial loading, which we're well acquainted with. We have direct shear, which is just the average load over the shear. We have the actual shear formula that we find here. Okay, on a beam, we have the bending normal stress. This is the bending shear stress. Okay, and then we have the torsional load. Okay, so we have axial loading, direct shear, bending stresses from the flexural formula, shear stresses due to bending with the shear formula, and then torsion due to the torsion equation. So all of these cases can be happening at once. Okay, in an element, and we call that combined loading. If we have a curved beam, this formula changes a little bit for the inner and outer surfaces like this, but these are the combined loading equations, and that is a summary of the stresses that we get in a material. Okay, so how do we figure all this out when we have a real problem? Well, you make some assumptions about the materials and make sure that those assumptions are reasonable. Okay, if you have a material with different properties in different directions, then you're going to have to consider that and take a look at, if you're working with composites, these equations are not going to directly apply. And then we do what we always do: we draw free body diagrams, we find our applied forces, moments, torques, and etc. And then we find the distributed loads on the parts geometry and determine which parts of that design are the most heavily loaded. And then we take a look at the stresses and find out where the highest combined, where the combined stresses are the highest. And then we draw the 3D state of stress for each of the elements. And then we'll find the applied stresses, and then we calculate the principal stresses and maximum shear stress. And that's what we're going to talk about in the next lecture. And then we can calculate the deflection of the part and make sure that the part doesn't experience stresses that would cause failure, or deflection that would cause a design failure where you have excess deflection that you can't, that would violate the design requirements. This is a good example in your book. It just shows how, if we look at the state of stress at points A and B, because of how we calculate those formulas and look at those cross-sectional areas, these stresses are not going to be the same as you would expect. And so this has combined loading. So we have axial loading. We have a moment arm here from this applied force, which causes torsion. We also have bending due to this load that causes this member to bend. And then we look at the stresses due to this load, this combined loading at A and B. So go through this example in your book and see the state of stress at each one of these points using these formulas, and then we can find the principal states of stress. So this is all review. So if this is something you think, oh no, I have no idea what's going on here, then go through this example and it should bring you kind of up to speed to where you need to be for this class. All right, so the next class we will talk about taking those stresses that we find and using Moore's circle to find our principal stresses. And this is all required because where we're going is we want to introduce our failure criteria, our static failure criterias, and then we're going to go on to the dynamic failure criterias, but we have to make sure that we have the fundamentals right. So we'll go ahead and end this lecture here, and I will see you in the next lecture where we show how to take the forces that we apply and use Moore's circle to find the principal stresses.